Hi Wildcats, this is Unit 4, Focus Question 6, where we will be looking at what actually causes magnets and magnetic fields. So let's just start by saying we're going to talk about this solely as magnetism, but now we understand that electromagnetism, electric fields, electric forces, magnetic fields, magnetic forces, they are one and the same. We call them different things because it's convenient to study them separately, but in reality, they are a single force, the electromagnetic force, electromagnetic fields. So, with that being said, let's take a look at this. Um, okay, so let's start by talking about why do things act like magnets anyways, and that comes down to their atomic structure. So just like we saw with electric fields, it has to do with the electrons and how their outer shells are filled. So you may not remember in great detail, but these are orbitals, and so electrons fill these orbitals, the 1s orbital, 2s orbital, 2p, etc., etc. And then the way we fill them in is one uh, by their spin, right? So we can say electrons spin one direction or the other, clockwise, counterclockwise, and we fill them in by spin. And we have to fill them all in before we can go back in one direction before we can fill them in the other in a given orbital. So in this case, the 1s is filled, so one spinning clockwise, one counterclockwise. 2s is then filled clockwise, counterclockwise. And then in 2p, if we have each one of these is an electron, so it would be 1, 2, 3, 4, 5, 6, 7. So if we have 7 electrons, we fill in 1s, 2s, and then we have 3 left in this 2p orbital, and we fill them. They're all spinning the same way. And so um, that spin causes a magnetic field. So when electrons are paired, like in the 1s orbital here, one spinning clockwise and the other spinning counterclockwise, they cancel each other out. So that spin moving electrons, just like we saw when we looked at moving charges cause a magnetic field. Well, moving charges, in this case, the charge isn't moving through like a wire, the charge is just moving by spinning around. And so when it spins, it creates a magnetic field. But since this one is spinning clockwise, we would have the north direction up here. This one's spinning the opposite direction, so it's south up here, and these then cancel each other out. So this would be non-magnetic. But when we have things with orbitals that are unfilled entirely, we have it results in a magnetic field. So let's take that back for 1 second. Spinning electrons, moving electrons create a magnetic field. When they are together in an orbital like this, they cancel each other out, so non-magnetic. But lone electrons in an orbital like this, all spinning the same direction, would cause whatever this atom is to have a very teeny tiny electric field, electromagnetic field, i.e. it acts like a magnet. Okay, so when electrons are paired, their magnetic fields cancel out because they spin oppositely. When I have electrons unpaired, there is a small magnetic field produced by those atoms, and therefore that atom can act like a magnet. And that occurs at the atomic scale, but as we'll see, that can build. So here are some different examples. Beryllium. Beryllium has 4, its atomic number is 4. So if I fill these electrons in, 1, 2, this is the 1s here. So the 1s orbital is right here. I fill this in 1, 2, 3, 4. I have no, and this is 2s, 2p. There's no unpaired electrons, and therefore beryllium is not something that is magnetized or acts like a magnet. Boron has 5, so 1, 2, 3, 4, 5. This one could possibly be slightly magnetic because it has one lone pair electron. And as we go up, we see that there are more, right? So carbon, nitrogen have more unpaired electrons. Even oxygen has unpaired electrons. And as a result, these types of atoms with their unpaired electrons spinning in the same direction, these types of atoms can act like magnets. Iron, which is maybe the thing we're most familiar with acting like a magnet, right? Iron nails, even the magnets we've been using in class have been made of iron, has 1, 2, 3, 4 unpaired electrons, so it can fairly easily act like a magnet. Other atoms like iridium, completely filled, so it doesn't become that. Even aluminum, right? Aluminum does not easily or isn't something that we think of when we think of a magnetic material, but it has a lone pair electron, and as we've seen in class, even aluminum, when put by a really strong magnet, can act like a magnet, and that's because it has this lone pair electron. So materials with unpaired electrons are magnetic, iron, but even oxygen and aluminum can be. And so I found this picture. I think this is a good example. This is liquid oxygen. And if you pour liquid oxygen between two really strong magnets, you can see that it sticks there. Well, the reason it sticks there is because those oxygen atoms are acting like little magnets. And so we can, even something like oxygen with its lone pair electrons can become magnetic. More unpaired electrons become a stronger magnetic attraction. So aluminum has few, but if we put it by a strong magnet, it can be a magnet. Iron only or has many unpaired, and so we don't really need a strong magnetic field to get it to act like a magnet. And that's why iron is easily magnetized. Okay, um, taking that one step back or bigger. So now I have individual atoms that act like magnets. Turns out inside of a material, there are these regions called domains, and you can actually see them. So this is a representation in the picture off to the right here. This is a micrograph where we look in, and you can see that each one of these little regions, like here, this is a domain, this is a domain, each one of these is a domain, a specific region where all of the atoms are kind of aligned in the same way. So these are all the same atom, but their alignment is slightly different, each one of those domains. And so in a substance that's not a magnet, all those domains are pointing basically in a random direction. And because they're all random, they cancel out. So this one's going to the left, but over here there's a right. This one's going up, but over here there's a down. And so all these random domains basically cancel out, which means they're not aligned. This object isn't acting like a magnet. There's no net magnetic field. But if I could get all these domains to line up in the same direction, now all of a sudden they would all be pointing, say, north, and this material could suddenly become a magnet. And so that is actually what's happening when we take a material that isn't a magnet and make it magnetic. So, and that goes back again. Atoms that have lone unpaired electrons can easily line up like this. Other ones are much more resistant to this. So here is just random alignment of domains. If I take them and apply a magnetic field to them by holding them by a strong magnet or electrifying them so that their domains align due to the electric current, an electromagnetic field that results from it, suddenly it can become an atom. So this is a nail, right? And this nail has been put next to a magnet and by an iron nail. And because the atoms have many lone pair electrons, they can easily move and become aligned. And so as a result, each one of those atoms acts like a little magnet and is aligned. And now overall, this nail can become a magnet. And so here is like the random spin of each of those domains and atoms, and now they've magnetized, so they're all pointing in the same direction, hence a magnet. And so that's basically what's happening in each of these pictures here, is that when domains align, that can result in an object that was not a magnet acting like a magnet. Okay, so we've looked at this before. Earth has a magnetic field. Earth acts like a magnet. Why? There's got to be some explanation. Well, we understand now that it has to do with moving charges. And so inside the Earth, it's magma and liquid and all those other things. We have an iron core, and that is spinning. And so it is that, right? What do we have? Instead of single atoms spinning around, now we have a whole bunch of atoms, iron atoms, and other atoms spinning around here, moving charges, create an electromagnetic field. And so why does the Earth have this magnetic field that we saw it does by using the compasses? It is because inside the Earth there are moving atoms, charges in the core and in this liquid mantle, that each produce their own teeny tiny little electromagnetic field, which then is cumulative, and there are so many of them, we can create a giant magnetic field all the way around Earth. And so we said before, that saves us from the sun. So as these electromagnetic radiations and high energy particles come from the sun, they interact with our magnetic field and are driven away. Some of them are driven down to the poles, where they then interact with the atoms in our atmosphere, which causes them to give off electromagnetic radiation that we see as light. Energy comes in, it bounces those electrons off, right? So now we're going back to electromagnetic radiation, and that energy given off in the form of electromagnetic radiation is what we call the northern lights or southern lights, or aurora borealis. So it's just kind of, aurora borealis is a great example of how moving atoms inside the Earth create an electromagnetic field. Electromagnetic radiation coming from the sun interacts with it, is driven to the poles where the magnetic field is the strongest, right? It pulls those in, and then energy from that electromagnetic radiation interacts with the atoms in the atmosphere, giving off other electromagnetic radiation, which we call light, and we can actually see. So it's a good way to kind of pull together a bunch of different ideas that we've talked about. Okay, so we talked that electric current causes magnetic fields. So we saw that spinning atoms create moving atoms, or moving electrons can become little magnets. So now when we have electrons moving, we have a whole bunch of atoms, and therefore that must also create an electric current. So as the atoms move, they create an electric field / an electromagnetic field, and therefore around a wire that has electricity moving through it, we get a magnetic field. And that's how in class, when we turned on and off the electricity through a wire, we were able to actually make the compass needle move. So magnetic fields are produced when electric charges move through a wire. Current is moving charges. And so what we have, we call it a magnetic field, but we know it's really an electromagnetic field because those are one and the same. And so what we call, when you have an electric field, it creates an electric force. A magnetic field creates a magnetic force. We say that, but in reality, these are electromagnetic fields interacting. Same thing, we just call them different. And so we can look, there are different variables that can affect how strong a magnetic field is, and that can be current and distance. So those relationships are pretty straightforward. B is the symbol for magnetic field, measured in Teslas or Webers. And it turns out the farther you move away from a wire, the weaker the magnetic field. So that would be an inverse proportion. And the more current or electrons I send moving through there, the stronger the magnetic field, which makes sense. If one atom moving through creates a teeny tiny electromagnetic field, then moving a whole bunch of atoms or increasing current would result in an even larger magnetic field. And distance is something that we've seen consistently. The farther away you move in an electric field or magnetic field, the weaker that field has become. The same thing is true here because it's just the electromagnetic field. Okay, so if we put that all together, we end up with this relationship. I will save you the algebra, but in short, the magnetic field, or excuse me, a magnetic field is equal to, of a material with current going through it is equal to, we saw it's directly proportional to current, inversely proportional to the distance, and then turns out we need a constant, and that is called the magnetic permeability in a vacuum of a vacuum. Basically, it just measures the ability of a material to like become or have a magnetic field around it, and this is the number. It is 4 pi times 10 to the negative 7th newtons per amp squared. And then we need 2 pi. Again, we'll save, the math is probably a course or two higher than this Physics 1 course, so but understand that 2 pi is also here. So the magnetic field is equal to the magnetic permeability in a vacuum, which is this constant, which is on your equation sheet, divided by 2 pi times the distance from the wire. Okay. So this is pretty much what it works out to be. Here's an example problem. If we have 2 amps of current going through a wire, then we need to figure out what is the strength of the magnetic field 10 centimeters from the wire. So if we write down everything we know, current in this problem is 2 amps. Is 2 amps. Let's try that again. There we go. Is 2 amps. Let's see. The distance R is 10 centimeters, so we measured it with a ruler, but we need that in meters, so we need to convert. So there are 100 centimeters in 1 meter, so we cancel that out, and that would give us 0.1 meters. And so we have R, we have I, 2 pi is a constant, and this is the magnetic permeability of a vacuum, so 4 pi times 10 to the negative 7th. We could just solve for B is equal to, so 4 pi times 10 to the negative 7th, and that is newtons over amps squared, times current, which is 2 amps, all divided by 2 pi times the distance, which is 0.1 meters. Okay, units will cancel on this, but we haven't gotten quite into what a newton is and an amp and those sorts of things. So, but if we did get into those, you would see that these would cancel and we would be only left with Teslas as our unit. So now all that's left is to put this into our calculator and see what we get. So I know this won't be exactly the same without seeing it on the screen, but I'm going to kind of talk you through how I put this in my calculator. Maybe you don't need that. You can skip ahead. So I'm going to put in 4 times pi, and then you can just hit enter there if you want to. You should get a value, and then take that answer times the answer times 10 to the negative 7th. So as we've gone over, I like to break that down into smaller parts. So answer times 10 to the negative 7th. And then, so I have 1.26 times 10 to the negative 6th, with a little bit of rounding there. Take that times 2 amps. So now I have 2.51 times 10 to the negative 6th. And then I'm going to divide that by 2 times pi times 0.1 meters. And I end up with the magnetic field of, looks like 4.0 times 10 to the negative 6 Teslas. So that is a relatively small magnetic field, relatively. Okay, so hopefully that kind of helps you how you would walk through this problem, as well as just have an idea of how how magnetic fields occur due to the atomic structure of the materials that make them up and how those atoms add together into domains.